A weak eval set makes every retriever look good. I'll build hard negatives in Python, so your RAG tests actually catch ranking failures before they reach production. This is the pattern you'll be able to implement by the end, which finds confusable but wrong documents for a query using a known correct document. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Hard negative mining matters because a naive evaluation often misses real errors. If your test queries all have clearly different wrong answers, any retriever looks perfect. In contrast, hard negatives are wrong documents that look a lot like the right one. They reveal ranking weaknesses earlier. Practically, that means your retriever must not only be generally good, but must prefer the correct passage over near misses. That reduces surprises in production and helps direct model fixes to where they actually fail. Think of the intuitive idea as a simple game. You have a query and a true document. You rank all documents by a semantic similarity. Then, you pick a distractor that scores almost as high as the true one. That distractor is your hard negative. Adding a small lexical filter keeps the distractor on topic. The goal is to create test cases that make the model choose carefully, not guess easily. Strengths are realism and focused pressure. Weakness is the need for a decent semantic score to begin with. We will build a tiny pipeline that shows the full loop. It will create a small corpus of short passages. It will show a naive lexical ranker, then a cheap deterministic semantic embedder, then how to pick a close semantic distractor, then how to require lexical overlap, and finally, how to report whether that distractor actually breaks the semantic ranker at rank 1. This keeps the example small and concrete, so you can scale it later. Now, we make a minimal lexical retriever to see what easy matching looks like. This snippet builds a tiny lexical retriever and returns the top match. The dictionary docs stores short passages, while Q holds a single query and its known correct document ID. The function toke uses Python regex findall to lowercase and split into word tokens, giving simple sets we can intersect. The variable Qt caches query tokens, and reg sorts document IDs by set overlap size with Qt. A larger intersection means a higher lexical score, so the first ID and rank is the top match. The printed top ID and overlap confirm what the naive overlap ranker would return, and how strong that match is. Next, we add a deterministic semantic scorer that uses a tiny embedding trick. This example adds a deterministic semantic scorer that can disagree with lexical overlap. The function embed turns text into a tiny vector using the MD5 hash bytes as a source, scales values into a range, and L2 normalizes for stability. The lambda sim computes cosine via a dot product between the query vector EQ and each document vector. The list rsem orders document IDs by semantic similarity descending, and goldrake finds where the known correct document appears. Increasing the vector length by consuming more bytes from the hash generally sharpens separation, while fewer dimensions blur differences. The printed gold rank sem and top ID sem reveal whether semantic ranking promotes or buries the correct passage. Now we mine a hard negative among the top semantic contenders. This code mines a hard negative that most confuses the semantic ranker. The variable cand takes the top k non-gold candidates from rsem, focusing on highly similar distractors. The vectors epause and the score spause capture the gold passage semantic strength against the query. The list snegs holds each candidate with its similarity, and max selects the most competitive distractor as neg ID along with its score sneg. The difference gap measures how close that negative is to the gold in semantic space. Smaller values mean harder negatives. The printed hard neg ID and sim gap tell you which distractor is toughest and how thin the margin is. Next, we make sure the negative is on topic by checking lexical overlap. This snippet applies a lexical overlap filter to keep only on topic hard negatives. The parameter min overlap sets how many shared tokens the distractor must have with the query to be considered relevant noise instead of an off-topic mismatch. The variable OV counts token intersections using the earlier toke function and the query tokens QT. The Boolean keep decides if the mind neg ID passes this filter, ensuring your negatives pressure both semantic and lexical cues. Increasing min overlap tightens acceptance to only highly on-topic distractors. Reducing it admits looser, possibly irrelevant items. The printed kept by overlap tells you if this negative is suitable and why. Finally, we use the mind negative to expose an actual ranking failure. This example closes with a tiny baseline that exposes ranking failures using your mind negative. The variable semtop is the semantic ranker's first result, and semfail flags if it misses the known correct document. The variable hard at 1 checks whether the specific mind hard negative occupies rank 1, signaling a realistic confuser. Together, these values show if your evaluation set is capable of catching real errors early instead of passing easy cases. Tuning, mining, and filters upstream will shift both indicators measurably. The printed semfail at 1 and hard neg at 1 make the failure visible and attributable to a concrete distractor. In a real project, this same pattern scales. Replace the tiny embedder with model embeddings. Replace the small corpus with your document store. And swap the lexical filter for a more robust tokenizer. The core loop remains identical and gives you actionable test cases. Recap. What it is: hard negative mining finds wrong documents that closely mimic the right one. When to use it. Use it when you want your RAG evals to catch realistic ranking mistakes, not only trivial mismatches. One caveat: you need a reasonable semantic signal first, or your negatives will be random and unhelpful. Wrap, punch. Next step: tune the semantic embedding dimensionality, or the candidate window size used when selecting top K distractors. That single change often makes mind negatives much harder and more informative. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.